If you've got questions about the data science program or the 4+1 program with regards to advising, definitely reach out to me because I happen to be the advisor for both those programs.
Oh, really?
Yeah, I'm the advisor for three data science concentrations, the 4+1 program, as well as the CDS graduate program. Yeah,
Does Tableau have a 4+1 program for data science?
it does.
Oh.
So if you're in for computer science and data science, they have, as well as I think there's a computer science and mathematics major that can also go into CDS. There's a few different what are called memorandums of understanding, which is what the plan is. For those of you who are unaware of what the 4+1 program is, if you've got a 3.25 GPA, you can meet with me about that. And what it is that typically a master's, you get your master's and then you go get your bachelor's. Sorry, if you get your bachelor's degree, you can go to a university, spend on a 2-year, 30-hour program for a master's degree. 30 hours is in 30 credit hours. Also note that basically you don't typically take, I think I've taken like maybe 9 hours worth of courses at most when I was a graduate student. So it's the expectation and workload is a bit different for the hours, but regardless, the way that the 4+1 program works is that in your program you have a list of electives that you have to take. What you do instead is that you take graduate courses as your electives, and so they double count as for both master's credit and for undergraduate credit. It's a pretty good option if you're looking at the graduate degree. I would not recommend it, however. I may or may not recommend it, however, if you're actually interested in going for a PhD, because there's this misconception that you need a master's to go and get a PhD. This is not true. You can apply directly to a PhD program and simply collect your master's along the way, so to speak. Because a PhD can take like 5 years on average, with a mean with the bell curve extending down to 3 to up to 7. I only know one person who did that 3. He says he regrets that. On the flip side, he does make like $500,000 working for Google, so because more money, more problems. You'd think so too. But money doesn't buy you happiness; it only rents it. So, there's actually side note. There was a psychology study I think done a decade ago, and the prices may have changed, and it also depends on where you live. But it was basically at what point does the rate of return for happiness per money start to have a significant decrease? And the answer was around $80,000 at around the time, on average for the United States. At that point, beyond that, the marginal happiness per dollar increase to your salary started to really, have diminishing returns. And if you think about that, that's pretty good. You've got the ability to basically eat out as well as, basically when you want to, so long as you're not going to like super fancy restaurants. You've got the ability to basically maintain home and have security and build up a nest egg with, basically once you have those basics, you're actually fairly satisfied. Most of us are. So regardless, that's just kind of a side note there. Anyway, so yeah, advising questions, and even if you don't have questions about CDS or whatnot, or the data science in general, please feel free to reach out to me. I can give you advice on other things, in general. I might end up directing you to your appropriate advisor, but I can answer some basic questions definitely. Speaking of basic questions, we probably have basic questions like, when's the next exam? Probably not next week, but almost certain. But I'm thinking probably on the 9th. I'm thinking probably the 9th would be the next exam. I think based on the schedule that I have put forth, that's a good balance of when to do things. It's also just it also just simply lines up then. Also note that Monday is the day of the eclipse. So And normally I would do an exam review that day, but also I don't know, but I'll be out. I'll check the schedule. I'll either do a Zoom overview of the practice exam, or I'll just simply link you to my walkthrough from a previous semester. But you will get basically the walkthrough of the next exam. Here I'm gesturing to things, and then I realize, wait a second, it's not plugged in. So the 9th. Sorry. Very quickly, let's go over this. Okay. Okay, very quickly, let's go over this. Modules, we have, okay, just as a reminder, this extra credit exercise does exist for 30 points of homework points. So you can do that as long as it's done by the end of the semester. Just a reminder that it exists. Next is, we have this tree exercise that's due tomorrow. Hopefully people are doing fine with it. If not, I can, let me know, and I can push the due date back a few days, like 2 days or so. How do people feel about it? Do you feel like you need more time?
Can you just push it so we can have like Wednesday and like to talk to you soon?
Yeah, let's go ahead and at least push it back to Wednesday, and we will. Let's go ahead and at least push it back to Wednesday, which is pushing it back 1 day, and we will go ahead and change that time to PM. I think that's just an weird import from when these were from when I was in Tokyo. So okay, and then yeah, sorting out. So yeah, there's not any. So there are not. Note that with heaps, you should watch those videos. Okay, there's not any homework associated with it, just because the time. I feel like if I put one in there, it really messes up it really messes up with it feels like too much work if I do. Like it just adds one too many thing. So be sure to watch these videos on heaps. Let's go ahead and just shoot out the practice exam for you so that you'll have a way to review it, and I can thus give you the motivation to watch those videos.
Are heaps going to be on?
Yes.
Like a significant portion?
I mean, if you don't study it, you won't be able to get above a B. So there you go. Insert media course documents. That way, practice exam 2. Okay, and now exam 2 currently scheduled for 4/9. Publish. Okay, so there you go. Now I can pull it up, and thus here's your motivation for it. All right, same kind of thing. It'll most likely be out of 105 again, but the practice exam's out of 103. First page will look something like this, where we have data structures. I'll most likely make this multiple choice instead, where basically we have 4 questions where I give you a scenario and just simply choose which of the data structures is the best fit for this scenario. So like a router needs to hold packets in a buffer and deal with them in the order they appear. That's a queue, because there's no distinction between the relative importance of a packet or not. It's just simply you deal with things as they appear. That's a queue. Some tree vocabulary questions. Please review the quizzes that I have. The quizzes will actually be a very good analog to what's on for this kind of question, what's on the exam. Same with, draw pictures of these fulfilling the trees of this kind of requirement. Tree operations, this is almost word for word. This is the exact same question that occurs on the exam, only it will be different numbers. Right? Makes sense? So draw the binary search tree that forms after we add these numbers. 42 is inserted first. Using your previous answer, draw what happens when you remove the following. Questions about pre-order, post-order, and in order. Then here's your heap questions. Draw the mid-heap that forms after inserting these integers. Draw, using the heap you drew above, draw the heap after you remove an element, right? So, and then Huffman coding, which is which is the one to trip up students. It's not actually that difficult, but it makes sure you know how priority queues, which means heaps, work. Coding questions. This will be easier than what's on the exam. Write a recursive method that calculates the tree. Actually, it doesn't have to necessarily be recursive. It's just, none of these methods have to be recursive. It's just so much easier if you do them recursively. That's probably easier than what's on the exam. Checking if a tree is full. That's probably of the same difficulty of the questions that will be on the exam, of the coding questions. And then here's one that's a harder tree question that would be on the exam, checking if two trees are equal. And then a question almost for maths will be just almost certainly like this one, where you so return what characters occur in a string and how many times each occurs. Another question might be given a list of numbers, tell me how often each number occurs, right? Give me a frequency count of each number. Given a list of words, given a string, tell me how many tell me how often each word appears in the string. Ignore punctuation. Assume everything's lowercase and separated by commas. Okay. And then basically 10 points on analysis. So what are So basically, you'll have 3 coding questions: 2 on trees that will be related, and 1 on part A, part B. If you do part A, when you get to part B, assume what part A you do is correct. Okay, questions about big O will most likely end up in analysis. Like this one, was the worst case runtime of insertion deletion in a binary search tree and why, right? Okay, which is O of n, and I'll leave you to think about why that is. So basically, I would say 66% of the exam, about 2/3 of the exam is more of the conceptual kind of things as opposed to coding. So much different weight than the first exam, which is why I think students do better on it, because you don't have to spend nearly as much time coding. But the coding questions, you really want to make sure you understand basically how do you do it for trees, which is you tackle your base cases, tackle the cases where are really easy, and then when it's not easy, that's basically solve locally, then do your recursive calls. Okay. Or do the recursive calls, combine them, and combine their answers to get your answer. Okay? So once you understand how to do it recursively, it becomes very, very, very easy. Also, you're probably starting to think about internships. Okay? My advice to you is once you're done with this course, you're actually qualified to go and apply to basically any company you want, including the FANGs. Facebook, Facebook, Apple, Amazon, Netflix, Google, throw Microsoft in there as well. Any of those companies, you'd be qualified to go and try and at least go to the interviews and see what they're like, and possibly get it depending on your knowledge. My advice to you, though, is this website as opposed to LeetCode or something like that. You probably do want to try LeetCode, sure, that's fine. But I find Pramp to be a much more useful process, which is practice makes perfect. It's completely free. The credits are just simply so that they can Ponzi scheme their way to more invites, essentially. So you get basically you get a credit for inviting somebody and they accept an invite to it. So anyway, but what you do is that it's an hour block. It matches you with somebody who's at the same time as you. They give you a question to ask the other person, and the other person has a question to ask to you. They give you the question as well as the hints for it and the answer, so that you aren't completely lost with it. Binary search tree successor search, getting a different number, k-mest array sort. So these may or may not be problems that you feel like you're comfortable solving, but part of it is also getting over the whole social anxiety of showing that you're terrible at coding in front of another person. Once you do it a few times, you feel much less terrible at it. Okay. It's always, and it's good to do that because my first interview for doing a professor position went horribly because I had no idea how that worked. So, learn from my mistakes, do a bunch of mock interviews and stuff like that. That is my advice for you on that kind of thing. The other side is I'm a huge fan of Project Euler, mainly because it deals with because of the interesting questions they have. Really unavailable. Okay. For instance, things like this, that seem trivial, but then you have to think about how to do that. Like, work out the first 10 digits of the sum of the following 150-digit numbers. So here we have 150-digit numbers, add them up together, figure out what the first 10 digits are. In Python, this is no problem because you just simply make a for loop and add them all up. Okay, save it in a file, make a for loop, read line by line, add them all up. But what do you do in Java? Because these are longer than longs. So how do you end the world? The two answers are either, well, I guess I'd have to make a class. If you think about it for 5 minutes, first answer, number one, is I either need to make a class that handles adding arbitrarily large numbers, or idea number two, I should check if Java has a library that handles adding arbitrarily large numbers, which it does. It's the big integer class. So basically sometimes they're more theoretical stuff. Sometimes they're telling you more about how to deal with, sometimes these tell you about how to, get around these issues in your particular programming language. And finally, like some of these, like lattice paths, exist to teach you about dynamic programming and stuff like that, where basically, or memoization, right? This one is one that you can tackle recursively, but if you want to tackle it recursively, just like the Fibonacci problem, you need to have memoization, right? Does everybody understand what I mean by memoization? Or do you want me to give a 5-second explanation of what that is? Explanation. Memoization. So the idea behind all right. So I allude to it in my videos and in one of the quizzes, I think. Or maybe it's not a quiz I have for you guys. All right, yeah, this is actually very valuable information for you. So, do I not have my pen? Doesn't matter. Okay. The issue with Fibonacci, right? What is the Fibonacci sequence? Fibonacci sequence is fib of n is equal to fib of n minus 1 plus fib of n minus 2. Right? So or another way to put it, f of n is equal to f of n minus 1 plus f of n minus 2. So it's a sequence that looks like this: 1, 1, 2, 3, 5, 8, 13, 21, and then 34, and it goes on forever because there's no limit for that. Okay. So everybody understand the sequence? 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, right? And it just goes on forever. Okay. So typically we will see this coded as follows. This is actually, so first off, it's typically used pedagogically as your first example for what a recursive algorithm is, because the definition is recursive, even though it's terrible for a big reason. We don't actually want to implement it, because often if you implement it natively, it's terrible. Okay. Yeah, this is not what I expected to do today, but I realized that if you don't know what this, then this is something that you definitely should know. Okay? Okay. Public static int. Actually, let's make that long because these numbers get big very quickly. Fib, okay, And what we're going to do is we're going to say fib of n int and give me the nth Fibonacci number. The first two Fibonacci numbers, so fib of, so if f, sorry, so if, let's keep this simple. I'm going to refer to the first Fibonacci number as the first Fibonacci number, not the 0. If n is equal to 0, I'm just going to say that's 0. Less than or equal. Let's go with less than or equal to 0. Right? Makes sense? The nth Fibonacci, there is no nth Fibonacci, is negative Fibonacci number. So if n is equal to 1, n equal to 2, right? Those are our first two Fibonacci numbers, right? In the sequence, right? 1, 1. First Fibonacci number, second Fibonacci number, third Fibonacci number. So our base case is that if it's 1 or 2, we'll just simply say it's 1. Right? Make sense so far? And then otherwise, we just simply return fib of n minus 1 plus fib of n minus 2. Again, this does a good job, and this over here gives us a very good job of basically having to avoid going below 0, right? Right. So we don't accidentally get some issues from going for like if we're trying to calculate something. So regardless, so this actually doesn't. So there's nothing actually wrong per se about this algorithm. Except when you try to run it for a large for quote unquote a large Fibonacci value. So the 30th Fibonacci number gets calculated to 30? No, shouldn't be 30. Oh yeah, I told it to print out 30. Of course, this. Yeah, even. Don't worry. Like, you see, I make silly mistakes like that, too, all the time. That was completely unintentional. So 832,000, right? But as we go up, 40, let's run it. And it chugged for a second there. And now if I go up to 45, okay, run it. Definitely chugging there. Now, it's worthwhile to note why that is, okay, and why I've referred to this as a terrible algorithm in other, when I was referring to this. And the reason is because if we want to calculate I'm just going to say if we want to calculate the nth Fibonacci number, in that case, what we need to calculate is we need to calculate the n minus 1 and the n minus 2. In order to calculate the n minus 1, we need to calculate the n minus 2 and the n minus 3. To calculate the n minus 2, we calculate the n minus 3 and n minus 4 and so on and so forth. N minus 4, n minus 5 over here, right? And to do n minus 2, we have to also do n minus 3 and n minus 4 over here, okay? So note what the thing is that if I calculate this over here, I then have to go back. When I get to the right side, I have to recalculate it n minus 2 here, and I have to recalculate it. And if I calculate same thing with n minus 3. If I calculate n minus 3 here, I have to recalculate it also here and here. Make sense? I have to do a lot of recalculation over there. That's no fun, okay? It's actually terrible. It's actually not just terrible, it's really terrible. I'm surprised that finished. 50, when it gets to 50, it's not going to finish the runtime because this is an example of an algorithm that is approximately close enough for us to say that it is O of 2 to the n. which is exponential runtime, which is about as bad as it gets. This means for every time I increase n, it's going to take twice as much work, right? And it's very easy to see by just simply saying I want to calculate n plus 1 now, which means I have to calculate, if I want to calculate n plus 1, then I have to do the n tree, and I have to do the entire n minus 1 tree as well. So it's not exactly 2 to the nth, but it's close enough. Where basically, where every time we increase it, it does about twice as much work. So how do we get around that? Well, the answer is by trading off some memory, by creating an array, we can actually get this all the way down to linear time. How? Well, what's killing it? These repeated calculations that we've already solved. So what we'll do is that we will just simply, what we'll do here is that we will, instead, I'll create this private private long, private static long fib, but I'm going to create it with a int n and a long let's call it memo. So memoization means we're just going to simply track our answers as we solve them, so that as they occur, so if it's there, then, if it's already solved, then we just if we've already solved it, we just look it up. Otherwise, we solve it. So how do I do that? Well, what I'll do is I'll just simply say return. I'll change the original fib call to return fib n new long, and it will be, technically it only needs to, it will be n plus 1 long, because I'm going to waste that 0 index for easy math, okay? Right? Because that way I don't have to worry about arrays starting at 0, right? The n plus 1 is so I can say the 30th fib number's at index 30. And who cares about that one wasted array slot? That's fine. Okay? So what we do over here is we now do the base cases as normal. Actually, if I'm going to do this properly, I will just simply say, let's go ahead and actually do this properly. If, I might end up wasting the first two, that's fine. If n if n is less than or equal to 0, just like we had, return 0, because we don't want to array out of bounds. Else, if n is less than or equal to if n is less than or equal to 2, return 1. Okay. And then finally over here we do this call, which requires a few if statements, which is basically if memo. I'm going to have n minus 1. Let's see. So n minus 1 is equal to 0. There's probably a cleaner way to do this. Int n minus 1 is equal to 0. Int n minus 2 is equal to 0. Okay. If memo of n minus 1 equals 0, then we need to solve it. Right? If it doesn't have an entry, we need to solve it. N minus 1 and our memo. Okay. n minus. So if we haven't solved it, we need to solve it. Also, these should be longs apparently, because it is a long. Else, if we have solved it, we just simply retrieve it from the from this value. And now we do that for n minus 2. There's probably a quicker way to do it. Basically, we're just simply asking, have we solved this yet? N minus 2, n minus 2, and then if n minus 1, if memo of n equals 0, if memo of n is equal to 0, basically if we've not solved what's in our memoization yet, basically if we haven't solved n yet, I suppose I have to, actually we should just basically add that up here. If memo of n is not equal to 0, that's what's going to speed us up. If memo of n is not equal to 0, return memo n. Make sense? So if we've already solved, so suppose we're solving the nth Fibonacci number. If we already have it written down, we return it. That's a base case. That's why it's going up there. Otherwise, we'll calculate it. What we'll do is that we have to calculate this last one. And then we have to calculate the n minus 1, we have to calculate n minus 2. Okay? And then what we'll do to calculate those is once we calculate those, we'll say memo, because we haven't done it yet, memo of n is equal to n minus 1 plus n minus 2 return memo n. Make sense? So let's look at that in its glory over here. Basically, if it's trivial, return it. If it's trivial, return it. If we've already solved it, return it. If we haven't solved it, solve n minus 1, solve n minus 2, store the answer, and return it. And now if I run this, let's see, 1, what did I do wrong? What did I do wrong here? It says 1, so I did something wrong here. Memo of n is n minus 1 plus n minus 2. Return, oh, I didn't actually calculate n minus 2. Oh, I didn't actually calculate n minus 2 at any point. There we go. My bad. N minus 1, n minus 2. And there we go. It solved it in a relative blink of an eye compared to the fact that it hung last time, because it just simply, any time that we had something we already solved, we just return it, right? So now we can go arbitrarily large. And so the key to solving something like this is that we basically create an array, or in the case of something where it's like a grid, you might have to make a 2x2 array. But basically, anytime you solve something, you write it down so you don't have to make repeated recursive calls. So and then the runtime is as many slots as you have to fill in the array. Okay, that's memoization. Basically, it's doing recursion from the top down still. Okay, and the difference between recursion and with memoization and dynamic programming, as you'll learn, is that recursion with memoization is still a top-down approach where you look at base case, and then solve from like the top down, whereas dynamic programming is solving from the bottom up. Okay, so that is so that's the difference there, and. So if you've got like a recursive algorithm, that's something that looks like it should be a recursive algorithm, but suddenly the runtime is horrible, do what you're what you're learning to do for hash tables. Make a sacrifice of the memory because memory's cheap. Takes a linear amount of memory, O of n extra memory to get O of n time, as opposed to the other one, which will actually use an exponential amount of memory because it's a stack. And that takes forever. Okay. So that is recursion with memoization. Will you ever have to use this on the exam? No, but it's useful for your interviews, and it's like this is just a technique that you should know, like recursive backtracking. It's very helpful for getting the runtimes under your control. All right, I'm going to go ahead and stop recording because I want to go and make sure I can help people.